for no reason. Okay, so cool. Well, which ones are giving you trouble?
The first one, I couldn't figure out 1C.
1C. Okay, that's
Yeah.
just ester hydrolysis. So you have an ester there. Treating it with water and acid will do the reverse of the Fischer esterification, right? So that one's just going to split that up into the carboxylic acid and the alcohol. And in this case, it's going to be on the same molecule. So we can take a look at it. Let me.
Yeah, because I did the mechanism for that, but I only got like one OH, and then I actually got two OHs.
Two OH. Well, you should have a carboxylic acid. Okay, let's go ahead. Let's take a look. Okay, so we have sorry, that should be. We have an oxygen there, and then we have the carbonyl, right? So, that's terrible. But what's going to happen here is you're going to protonate. So you have acid, right? So we're going to protonate our carboxylate, or our ester rather, sorry. That should be a line, but there we go. Protonate that. So we end up protonating our carbonyl. And this again should be an oxygen there, but I'm being lazy. Water comes in. That's where the other OH comes from. It's from water. It's going to come in here. We're going to make a tetrahedral intermediate. So we have, okay, I'm going to make sure that I actually put my O in here this time. Okay, so we have OH, we have OH2+, and then we have the rest of this cyclic thing, right? What's going to happen now? I'm going to just do a proton shift. But technically, if you want to show the mechanism for this, it would be several steps, right, to move the proton around. But suffice it to say, if we move it here, we can now close down. Let me use blue. We can close down, pop this open. And if we think we have 1, 2, 3, 4, 5 carbons in between, so we're going to have, we have this, that's carbon 1, the purple one. We have 2, 3, 4, 5, and then we have OH on that one. And then we just have to deprotonate, so we have water come in and take that away. And so we end up with the hydrolyzed product, which is the same thing, but just a regular carbonyl. All right, so that's where that extra OH comes from, is from water, as this thing hydrolyzes. So you will get a carboxylic acid and an alcohol out, and so you have that. Is that what the answer key has?
Yeah, that makes sense. I don't know why when I like closed in the oxygen to make a double bond, like
you
picked
lost.
the OH out.
Okay, yeah.
Well,
Well, yeah, so it is equilibrium, right? So you could do that. It does happen, but it's not getting you anywhere because it's taking you backwards then to do that. So, yeah. Cool. All right, so hopefully that makes some sense. We can do more on this. We can spend the first half hour on this one if you like. Anyone just chime in with questions. Otherwise, Narek can keep asking him. I'm fine with that. So.
I could ask later, I guess. No
You could ask later. Oh my gosh.
I have a question for 2H on the same one.
2H. All right.
Have you learned that one? Because I couldn't figure it.
Yeah. It's just making an amide. It's a very slow process. It's not a great way to do it, but it's making an amide. So you have your carboxylic acid, and we're putting what, diethylamine. We're putting this in it. And so what happens is you'll make the amide out of this. So you're going to be replacing your OH with the nitrogen here. So the nitrogen comes in, and you have whatever's on the nitrogen will be part of that. This thing, this is a very slow process, terrible way to do it. Better way, of course, use either an anhydride or a acid chloride, because it's much more efficient, but you can technically get this to happen, yeah. Though it's reversible, so unlike if you use the other ones.
So I got confused. I thought when you did like the acid chloride and then to reactive.
Yeah, normally you would.
On a test, should we expect something like this, or no?
I tend not to give you inefficient reactions as things for me to have you solve. So yeah, if that works, I typically don't give just something as boring and inefficient, right? So, like for example, J would be the better way to do it, or I would be the better way to do it as well, right? Like, you see, H and I should give you the same product, but I is much more efficient of a synthesis. Although technically speaking, you'll need more equivalents of that diethylamine. Yeah, go ahead.
Which packet were these questions?
We're looking at the Si8 carboxylic acid derivatives. Mm-hmm. Yeah, so Narek, I would focus more on I, J, and K as being more realistic examples of what you'd see. H is not very good.
Yeah, I got those ones. Yeah. But then this one I just couldn't figure out.
Okay, yeah, it's just another way to do it, but it's a crappy way.
I had a question on 2F.
2F. All right.
She did something in her notes that was like note, like in the answer key. It's like note basically, and I'm like, what?
I'm sorry. Say okay. What? Okay. Let me look at the answer key. Let's see what it says.
Yeah, like I didn't know what it said.
There's probably no reaction, but let's see. Yeah. Oh no, F. I'm sorry. No note. Okay. Yeah, you make the thing. Yeah, there's no yeah. So yeah, you're putting a base in and then you're putting an acid in, so nothing's gonna happen. Yeah. So methyl lithium is a CH3 with a negative charge. Could be a nucleophile, but you have a very acidic proton here. So just going to grab that off. And then you use H3O plus, you put the proton right back on. So you don't do anything. Yay.
Okay.
Yeah.
Would you write trick questions like stuff saying no reaction or?
Don't give me ideas, Eric.
I know I already gave you a lot of ideas.
So yes. And by the way, you'd get the same with a Grignard, right? Like if you try and use a Grignard on a carboxylic acid, if you're just using one equivalent, nothing's gonna happen. Right? It'll just deprotonate, and that's it. All right. What else would we like to do? Anything else on this fun worksheet?
I had another question on number 8.
All right.
Well, for the last 3 problems, what is like the NaOH and HCl do?
So the NaOH, you're going to hydrolyze this thing, presumably, and then HCl is there to reprotonate afterwards. Because when you hydrolyze in basic conditions, you end up with that carboxylate, and then the HCl is to take you from the carboxylate to the carboxylic acid. So like, here, I keep forgetting we have the thing here. So I'll just do the quick and dirty as written. Another film. Okay. NaOH with heat and all that will you'll end up with this, right? The HCl just turns you into the carboxylic acid, and then you have NaCl as your other product. So because the carboxylate may be hard to isolate, but the carboxylic acid is easier. And then of course you end up also losing out your amine there.
So quickly, can you do E real quick?
E, let's have a look. All right, yeah, it's another hydrolysis. So, so remember, ester hydrolysis can be done in either acid or base. What do we have? Sec butyl. Okay. NaOH will cleave here. It's the same idea. We're cleaving that bond, so we end up with. You end up with the carboxylate and your alcohol, and then HCl should go ahead and take you back to the carboxylic acid. And again, I guess your other side product would be NaCl, but who cares about that? I guess Charmras would, but I don't. So. So all of these were hydrolysis reactions, right? Number 8. So gives you that sort of hint. And then Narek, did you say F as well?
Yeah, I couldn't figure F out. Yeah.
Okay, yeah. So this is the opposite of hydrolysis. This will make the ester, right? So we have. What is all this? Boop, boop, boop. Really, what happens here is, are we doing acidic? Yeah. Oh, go away. So let's just make it acidic already. We're gonna cheat. What happens is you'll have your alcohol come in, pop open, and we're gonna kick out the OH eventually. But that's what's going to be formed here. You're going to form a 6-member, or I don't know how many membered. 1, 2, 3, 4, 5. Yeah, 6-membered ring here. You're going to end up kicking out that other OH, the carboxylic acid OH, because that's what's lost in making an ester, right? So product-wise, you're making a 6-membered ring, where number 1 will be your carbonyl, number 6 will be the oxygen, and then we had all those carbons in between. And so it looks like carbon 2, we had 2 methyl groups. And then carbon 5, we have another methyl group. So that's what we're looking at for this one. So it's intramolecular. You're taking your alcohol that's far away. You're making the ester onto your carboxylic acid. And then you then just do your protonations, deprotonations.
Okay, thank you.
Mm-hmm. Yeah, the intramolecular ones are always a little bit tricky. And the fact that it's on a wedge just scares you. Yeah, what's up?
What did you use for this one? It was, you said, a reverse.
This is just a Fischer esterification. This is 2F. This is...
Okay.
Mm-hmm. I suppose intramolecular, we can write that. So like 9A would be something similar. 1, 2, 3, 4, 5, but you'd end up with a 5-membered ring instead there. And B would be just the hydrolysis of that. All of these are pretty similar actually for number 9. Oh yeah, cyclic esters, duh.
But 9B would be the opposite of this.
Yeah, 9B would be the kind of what we did here. Kind of.
Okay.
No, not there. The first one we did. Where is it? Yeah, where we just cleaved that and made it a linear form instead of a ring form. So yeah, so like 9B would be just cleaving that ester bond.
Question for number 10, like the synthesis part.
Mm-hmm.
Like the things that she wrote are like different than what I wrote, so I don't know if
Yeah.
like
I mean, go
what
ahead
I
and
did
share
is
if you like.
right.
We can have a look. Because
Uh,
she even mentioned, there's more than one solution for some of these. So if you want, you can go ahead and share, and we can take a look. Or if you have just like specific, like, hey, I tried this, would this work? And
yeah, could we do it like that? So I don't know how to share the system on the computer.
Oh, okay. Then yeah, well, tell me which
Like,
one, and what you're doing with it. I'll take a look.
So for number 10A,
10A, okay.
the first one,
Uh-huh.
I first did CmNO4 to make the carboxylic acid,
Okay.
and I did SOCl2 to get the acid chloride,
Okay.
and then I did LiAlOT butyl H with H2O to get the aldehyde,
All right.
and then I did the H plus and then NH2 with a isopropyl group with NABH3CN.
Okay. That's a little bit extra work. You can technically once you have is it 4 carbons? Yeah. Once you have this thing that you said how to do, you oxidized and then did your acid chloride, thionyl chloride on it, you can just take this and put this thing in it, 2 equivalents, and you're done. You don't need to do all the reductive amination and all that fun stuff, because oh, I'm sorry. We do. Oh, I lied. I'm sorry. Once you have this, then you can use just lithium aluminum hydride. That's probably the easier way to do it, because then that's fewer steps. Because if you take this and do, what did you do with this, by the way? What was the next step?
LiAlOT butyl H with H2O.
Oh, because you made the aldehyde out of it. Okay.
Yeah, I made that.
Okay, and then you did the condensation with this thing.
Yeah.
Okay.
I also used NABH3CN. I don't know if I'm
Yes,
supposed to
you
use
will
that or
need that
not.
because you're gonna need to reduce it.
Okay.
Okay. Yeah, that's technically one more step than just reducing the amide. So that would be okay. Just one more step is fine. Yeah, that would be okay. And then if you put the that would get rid of your imine to make the amine. Yeah, that would work. Oh, by the way, the reagent for this would be the fancy lithium aluminum reagent. Yeah, so that would work. What did she have? Let's see. What problem was this? 10A? Oxidize. No, I think her way, you end up with the amide. Yeah, you'd need to reduce that afterwards. So, yeah, because you would end up here with the way that she's done it. So, curious. Yeah, you need to get rid of the carbonyl, so. Anyways.
Can't you just do Clemenson?
No, Clemens is for ketones or aldehydes. Get out of here. Any of these other synthesis ones? Do you find them troublesome? Well, some of these are so easy. Like, look at G. Just throw water at it.
Like,
come on.
for work, for some of them are like really weird. Like, I don't know, it's like,
Well, okay, which one are you thinking?
actually, could I just share my screen? I think I got on the computer.
Yeah.
So that'll be easier.
That's fine.
Okay, so this one
All right.
for B would be correct.
All right. So what are we doing here? So we are making an amine from an acid chloride. So you make it the aldehyde. You condense with the amine and do reductive amination. Yeah, that would work.
Okay. Then would this be right?
Mm-hmm. That's reductive amination. Yep.
What about these ones?
All right. Hold up. Go up a little for D. Okay. So. Yep. It's they're really much the same thing, aren't they?
Mm-hmm.
So with the there's an easier way to do E. For example, if you take E, are there any others after this that you want to check, by the way? Or is this the last one? Okay,
Sure.
we'll come back to E otherwise.
Okay.
Because that one I'll show you a better way to do that.
Okay. And then, let me see. This one, H.
H. Okay.
Because like what I did was completely different than what she did for all these.
Okay, so you hydrolyzed, then made the S chloride, then did that. You can just probably put, since it's an ester, you can probably just throw the amine in there with acid and heat. Technically, you'd get your product. Okay. Is that what she did? But your way is not wrong. What number is this? 10H?
Mm-hmm.
Yeah, she just threw the amine with acid and heat. Yeah, that's an easier way to do it, right? But it would take a while. So, yeah, like yours would work. It's just more it's more steps, but it's a better reaction, if that makes sense.
Yeah, that was like if I do this on the exam, would I lose points if I do more steps?
No.
Okay. And then this is the last one.
All right. So we're making an anhydride. Oh, that'll be fun. Yes, you would need the carboxylate. Yep, looks good.
Is this like step correct? The last one?
Yeah, that would be the best way to do it. Yeah, to use a carboxylate and a acid chloride. Yeah.
Listen, I didn't know how to do this. I think that's it.
All right. So hold up. So 4 carbons. Oh, okay. Oh, I think Eric had this question. After this part, do an anti-hydroxylation using hydroboration oxidation, then oxidize to carboxylic acid.
Okay.
Was that problem mostly just not one of it was just 105, right?
That's all 105 stuff, yeah.
Yeah, okay.
Yep. You can't use NBS, by the way. You have to use BR2 and UV. And also that you're missing a carbon in that bottom molecule, bottom left. You start with 4 carbons, you end up with 3 carbons with the bromine, and then back to 4 carbons. So just be aware that you forgot a carbon. So.
Okay.
All right. Let's. What was that problem that we were looking at earlier?
I think it was E. Right?
Okay.
Wait, or
yeah,
no,
E.
H.
I think
Was
it was E. Yeah. So let's do an easier way of doing this. So, hop back to my screen, if you would, and we'll take a look. So how to go from OH to this? Yeah. So easier way. Do PBr3, gets you a bromine, and then you have your choices. You can do the Gabriel synthesis. Remember that's taking an alkyl halide as well as this phthalimide, and then hydrazine. That will give you your product. Alternatively, remember that you have the azide synthesis as well. Do you remember the azide synthesis? So you use sodium azide and then reduce it. So you have two ways of doing this. So you can either use the Gabriel method, using the phthalimide, and then the hydrazine, or you can use sodium azide and then a reducing agent, and that'll get you to your primary amine. So either way of those, and that'll be a little bit more efficient than going to a carboxylic acid, then aldehyde, then reductively aminating.
Professor, would Gabriel and Azide both only work with primary, or can you use one over the other?
So Gabriel must be for primary. Azide will give you a primary amine. Actually, both of these will give you a primary amine. So they will give you an NH2. Just remember that primary amines doesn't tell us about the carbon they're on. You cannot do Gabriel synthesis to make a primary amine on a tertiary substrate, if that makes sense.
Yeah.
And same with azide, because they both go through SN2 type mechanism. So you can't make an amine on a tertiary site. So since both these are primary, it's not a problem. You can do them on secondary as well. A secondary alkyl bromide will undergo both of these, but it'll still give you a primary amine, since the names mean different things. So.
Okay. So there's no difference, I guess.
Yeah. The only thing is you can't use the cyanide method here, right? Because that would give you extra carbon. So that would be the only thing that you can't do for this.
Oh, cyanide method is in like casein. Okay.
Yeah. Putting it instead of the turning the bromine to cyano, and then because I that would be for F. For example, for F, if you use cyanide on that, that's going to add that extra carbon for you, and then you just reduce it. Yeah.
I see. Okay. I have a question on J. So I'm pretty good with going from products to reactants, so I'm not really good at, or I'm not good at that part, like from J, seeing what the reactant
There's
is.
so many different ways to make this.
Exactly. So I looked at her answer key and I'm like, is that the only way we could do it? But
no, not at all. Oh my god, she's using an alkene? I would have thought you were using do it like a, I don't even know, like you could start with a I thought you would start with the ester or something and then oxidize it to the ketone. That's what I thought was happening. So yeah, I mean this one, because there's not given reagents, like you don't know what's happening. So in theory you can say, here's my reactant, or my whatever. Yay, I'm gonna oxidize this. I don't know, what should we use? Chromate?
Because I was trying to do this and I'm like, do we just make up our own problem?
Yeah, that would be a bad problem, right? Because you could do this, you could say I started with whatever. I started with an aldehyde and I made it a carboxylic acid. Woohoo! So yeah, I mean, there's 1,000 things that you could do to get this, so that's a badly written problem.
I thought I was just tripping out, but
well, given that she's it says provide reagents, I think she just forgot to put the starting material. So that's a pretty big whoopsie. So yeah, I would not have thought to go from an alkene. So all right, let's take a look at the amines one. Does anybody have any more questions on the carboxylic acids? SI.
No, just amines, I guess.
Yeah, okay, that's cool. Let's take a look at amines. Let me download the SI. Okay. Let's look at amines. What questions do we have on amines?
I had a question on number 3.
3. All right. Which one of these? Wow, there's like 50
Um,
problems for number 3. Wait,
Like fourth to last one.
hold up. There's 2 number 3s. Is it the first number 3 or the second number 3?
The synthesis one.
Providing. Okay, so fourth from the last.
Yeah.
Okay, so
Yeah.
it's the ketone going to that amine there.
So, almost. Yeah. Yeah.
Okay.
The one under the like bromine question.
Yes. Yes.
Yeah.
All right. So what did you end up doing?
I couldn't figure out how to get like the amine at the edge because like whatever I tried doing, it would be in the middle of the structure.
I
I
see.
don't know
I
what I
see.
was doing.
Yes, that can be a bit tricky, can it? So with this, let's go ahead and take a look. So we have a ketone, and we're making an amine with 4 carbons and an isopropyl group. So there's going to be a lot of steps required for this because, yes, moving a functional group from one carbon to another carbon is tricky, for sure. Did I forget a carbon? I did, I think. Yeah, we should have 4 carbons here. So chances are that these 4 carbons that I'm going to do in like blue, those should probably be these 4 carbons. So the problem is we have a ketone on carbon 2, but we need an amine on carbon 1, right? So we have a couple of things that we might do to this. First thing we need to do is figure out how to get that. Well, let's take a look at this backwards, right? So we have this amine. Assuming that blue part is the original molecule, we're adding the isopropyl group, right? So we might be able to do that by, say, doing... We can say maybe NaBH3CN. If we take this amine, we can get the isopropyl group on there. That's not a problem, right? So we can get that last bit on there. So now we're just kind of left with the blue part to put on, right? Sorry, not that last part. So that blue part is our original molecule. So we have to think, how the heck are we going to move that ketone from carbon 2 to get something on carbon 1 that we can make an amine out of? And so we have to consider, how are we going to move that? Best way would probably be to do a reduction and then an elimination to get an alkene. From an alkene, we can then make something that we can make into an amine, right? For example, we know if we want an amine there, we could take, say, the bromide and do either Gabriel or the azide synthesis will get us that amine. So how are we going to turn this ketone into the bromide? Well, we know bromide, we can get it there from 1, 2, 3, 4. If we have that, we can just say, we know how to do Anti-Markovnikov Bromination. And so if we think, okay, well, we have this, so we still have the ketone. To get to an alkene, well, we can get to an alkene from an alcohol by eliminating it, right? Since this is a Hofmann product, Since it's the Hoffman product, we're going to need to tosylate it and then use a bulky base like T-butoxide and heat, and that would get us our product. And then so we just need to reduce this. And so you can use a reducing agent. So that's a lot of work. I'm going to say she probably made a mistake on this one too, because that's what, 1, 2, 3, 4, 5, 6, 7 steps to get to that product. So yeah, kind of a pain in the butt. But that's how you would move a functional group around. So I get it. Yeah, if you try and go directly, you're stuck on carbon 2, but you need stuff on carbon 1. So you have to move a functional group is usually quite a few steps. And so do you see how that works?
Yeah, that makes a lot more sense.
Yeah. Pain in the butt type question. Oh, and I guess I rotated that first one too.
Thank you.
Uh-huh. Yeah, that's not a fun one. What did she put as her answer for this?
No answer.
No answer? She didn't do it? Wait. Oh, is this like where it doesn't align? Yeah, I don't see... Where
It's
is
like
this?
at
I don't
the
even see this.
bottom, I
Oh, is
think.
at the bottom? Okay.
I think it's like a mixed order.
Oh, okay. Oh, I don't want to find this thing. Okay,
It's
well,
on page 2, I think.
page 2? Oh, I'm way at the bottom. Okay. Oh, she didn't put anything. You're right. Okay, well, yes, that's fun. So, yeah, she's like, oh crap, this problem is too complicated. I'm not gonna do it. That's funny. I think maybe if you start with the acetone instead of this butanone, that would be a lot easier because you could just condense and then go from there. But yeah, too many carbons.
I also had a question on the naming part,
Okay.
because my numbers were all off.
All
Like
right.
my numbering on the carbons.
All right. Where's the
Like,
naming part?
things on the last page, number
Okay.
8.
Sure.
So the ones where like she already gives us the structure,
Okay.
do I not like start numbering on the like the pentagon on the very right, or no?
So since there's no priority functional groups here, you'd want to name whichever side will give you the most substituents. Like what's the like the best. You want to put your stuff on the lowest possible numbers, and you want to have the most have the lower numbers. So I assume with this she's going to start from the other side of the molecule.
Like she started with like in the middle of the structure, and I got confused.
On the middle of the structure? What do you mean? She starts
Like,
on the...
Like I think I forgot where she started. It was like on the right side of the.
At the
right
Or
side.
So the one that
or
gave you the
carbon.
lowest number of the chain, right? Which would be the
Yeah.
cyclopentyl group. Okay, so let's take a look.
Yeah.
So let me draw the molecule. 1, 2, 3, 4. Oh my god. 2, 3, 4, 5, 6. We haven't. Not even with stereochemistry. Come on, what is she doing? Okay, so we have a couple ways to number this, right? You could do the purple numbers. Or you could do the blue numbers. Am I missing something? Oh, I'm sorry, there's an additional carbon down there, sorry. Okay, hold up. I didn't draw it correctly. Okay. Sorry, there we go. Okay, so let's do the blue numbers. So we could start here. That would give us our 7 carbon chain. That's the longest one. or we could do it this way. So if we do the blue numbering will give us I don't know if we're going to do methylamino, or are we doing N-methyl? We can figure that out later. And then 7 would be cyclopentyl, right? So if we number it that way, we end up with 4, 5, and 7 as our locator numbers. If we do it the purple way, we have 1 cyclopentyl, 3 methylamino, or just amino, just depends which way we're going to name it, and then 4 ethyl. So if we look at the numbers, the purple ones are going to give us the lower numbers. So that's where we're going to choose to do the numbering from. And then so if you want to do the, you could name it as methylamino, or you can say 3 amino, amion, let's try that again. And you can also say then N-methyl. So you'd have to say both of those names or methylamino. So either way. And so if we're to put this together, I guess we can... Which way do we want to do it? Do you want to do it with methylamino or amino and N-methyl?
Amino and N-methyl.
Okay, sounds good. So we would say then 3 amino. Let's see, what's going to come next? A, then cyclopentyl. 4 ethyl N methylheptane. And so that would be how we would name this thing. And let's see, what did she have? N-methyl. Why did she have the N? Or that's alphabetically not correct. Okay, she's naming it as heptanamine. Oh, how weird. So she's using amine as the parent name. Amines do not have priority over alkanes, so there's no need to... You can do it either way. It's like you can say something is like isopropyl bromide or bromopropane. You know, you can make that choice. So she's choosing to have the amine as the parent name. And apparently I chose to have the alkane as the parent name, so no difference there. Okay, but the numbering makes sense?
Yeah, it makes no sense. I numbered the cyclopentyl too.
Oh, no, yeah, you wouldn't do that.
Yeah. So I had like 12 carbons.
You know, technically, the correct name for this is based off cyclopentane. If we wanted to be super correct, because cyclic alkanes get priority over alkanes. So, yeah. Here, I'll show you. I didn't even know it would be such a complicated name. Here, let's see. Okay, but go ahead and ask another question in the meantime.
Weird question. What's the point of saying N?
To show you that the methyl group is on the nitrogen.
Oh, okay. That makes... Okay, thank you.
Yep. Yeah, because N means nitrogen. Okay, so oh, what do you know? We are going to name this as an amine. Okay. What's the next question?
I'm gonna ask if no one has any questions. The one below it.
One below it. Okay. Yes, let's do it. And what else do we have? All right. Parent name will be... What's our parent name going to be?
Ketone.
Yeah, ketone, right? So that means we have to name starting at our ketone. So we have a heptan 2-one. Yeah. That's our parent name. Cool. So the only thing we have, carbon 3 has an amino group. And on that amino group, we have a methyl group and we have an ethyl group. And then 3 amino. So we just have to put these in alphabetical order. So 3 amino, N ethyl, N methyl, heptan 2-one.
So the way you would label ketones is just like the number of carbons at an AN.
So yeah,
okay.
it'd be because like our parent name is heptane.
Yeah, and
you
then
drop the E and add one, so heptanone would be the parent, and we put the locator number before the like suffix.
Gotcha. Okay, thank you.
Yeah.
I guess the last naming. No one has questions.
That's fine. We can do it. Let me just double check this. Okay, so we have that, and then oh, how interesting. Okay, sorry, the last one. Okay, so we got pyridine here, and with some chlorines and stuff. Okay. Methyl. Okay, so parent name is pyridine because it's a heterocycle, and those have standard names. So that's pyridine. That takes care of all of that. So we just have to put all the substituents on there. So the nitrogen is number 1. So we're going to have a methyl group on carbon 3 we have, what is that? What's the substituent is that going to be?
The chlorine and the methyl.
Yeah, what's that called?
Methyl
chloromethyl.
Chloromethyl.
Clono. Okay, that's just a disaster. Chloromethyl. And then you have the rest. Pyridine. Is the N come before the 4 or after the 4?
She put it before the 4.
Well, she also puts them way before, which is not correct.
Yeah.
Because you have to follow alphabetical order. So, like with that first one where she has N-methyl, it's got to go after the ethyl group. So, here, let's find out. Let's see. 3-chloromethyl N4-dimethylpyridine. Oh, it got mad at me because I didn't put my parentheses. Apparently it's...
Is that a website you use to check, or?
Nope. It's a several $1,000 piece of software that you do not get to know. Okay, why is this being such a pain? Okay, hold up. Let's just draw the damn thing. Okay, I'm gonna prove it to you. Just watch, I'm gonna be wrong, but I'll prove it to you. You're not gonna separate these. Oh, I see what the problem is. It's mad at me because this is a quaternary thing. She's missing a positive charge. Yeah. So there's 4 carbons on that, or 4 bonds to that nitrogen. So that's the problem with this structure. That's why it's being mad at me. So it would be a pyridinium. Yeah. 3-chloromethyl, 1,4-dimethyl. We have this weird lambda thing, pyridine, because it's pyridinium, because it's got the positive charge there. So, indeed. Okay, so what's next?
So I had a question from the notes we took on
Okay.
amines. The reductive amination part. So, like, when will we just like reduce it without the NABH3CN? Like, I'm kind of confused on when that would be useful. With just the NH3H plus and H2PT.
Hold up. Say again. So you're asking when to use that reducing agent?
Yeah, like when would that one be useful over the NABH3CN reducing?
So give me an example. So ketone, you're saying NH3, and then...
I'm going to just share my screen and then you can see.
Yeah, that's fine.
It could be easier.
Alright, let's bring this over.
So,
Looking at my own screen. Okay, there we go.
so when will we use like the 7th one over the 8th?
7th one.
Like
Okay, so you can use H2PT as long as you don't have anything else that's sensitive to it. So as long as you don't have any double bonds, triple bonds, ketones, aldehydes, anything like that, then you can use H2PT. So, but the cyanoborohydrin is useful because it doesn't touch anything else. It only reduces imines.
Yeah. Okay.
Yeah.
That makes sense.
So just a more selective reducing agent.
Yeah.
Cool. Back to my own. Okay. Oh, so yes, of course. Then you would end up with you'd end up with that, of course. All right, we got time for maybe like one more.
How about a problem that you think we should know?
Okay, let's take a look. Okay. These are boring. Let's see. That's pretty boring too. That doesn't even use amines. I don't even know why that's even on here. Let me look at the carboxylic acids real quick, because... Oops. A lot of these are not too bad. Only these were harder. Here, let's see. Let's look at some of her practice exams. 106 exams. Does anybody? Is this exam 4 for her? Yeah, looks like it. So okay, yeah. So here, let's name this thing. Yeah, that'll work. Okay. Which shall I show? Okay, here, let me draw the molecule, and then we'll go from there. So I'm looking at her exam 4. I guess that's all it's called. For one of the number 7 ones. So let's take a look at this.
Could you share the practice exam after?
Oh, of
After we're
course.
done.
Yeah.
Thank you.
Let's name this monstrosity. We have an easy name for this, but let's name it the hard way. So what's the most priority group this molecule has?
All of it.
All of it. Right, Ester, correct. Yes. So the priority group here is the ester. And how do we name esters again? So remember, esters have 2 names. Go ahead.
The 8 at the end.
Yes, we're gonna have an 8 at the end. We have the carbonyl side, and we have the alcohol side. Or so we have first name, second name, 8, right? So the alcohol side of this ester would be this thing. And so what is that? Actually, we're not even going to include the oxygen. What is this substituent? That's just benzyl, right? If we think this is benzyl alcohol, so that's the name, benzyl. That's all we have there. So now we have to look at the carbonyl side. And what do we have there? The parent there would be benzoate. But we also have a substituent on this thing, right? So we have, this would be carbon 1. That's going to be carbon 2. So we have 2-methoxy benzoate. So that's benzoic acid and benzyl alcohol come up to makes the top part, and then we just have that methoxy group on carbon 2. This thing is also called salicylate, but that's a common name. So benzyl 2-methoxy benzoate would be the like correct name for naming this thing. But if you said benzyl salicylate, you're not wrong. So do we see how we got those names? So this was the alcohol side of our ester. So whatever the substituent is on that side, the right side of our ester in this case, and then we name everything on the left side, including the carboxylic acid 8 name. So benzoic acid is our parent, kind of, our like sub-parent. Right, that's benzoic acid. So making it into an ester, you get benzoate, and then you just have to put your substituents on. And so you name them accordingly. And then if we had something like a chlorine on there or something, we would also include that as part of that ester. Although I'm not, yeah. All right, so do we see how that is? Oh, it is time. Unfortunately, I must go to my other class.